do not enter. This is a zone of high intensity radiation. Take a mask before you enter, or you could end up like one of these monsters. This is a green parrot. Crazy woman, why did you come here?
I was sent by the government to educate crazy high school children about radiation.
Oh, so you are the chosen one.
Yes.
Okay, come here.
Now that we have heard everything about historical context of the radiation, I will explain what is happening inside the nucleus and everything you need to know about radioactive decay. This is a nuclear process governed by physical laws, not chance or chemistry.
Radioactive decay? Okay, Professor. But what is a radioactive decay?
Radioactive decay is a spontaneous nuclear process in which an unstable nucleus changes into a more stable one. During this process, energy is transferred in the form of radiation. Radioactive decay is random and cannot be predicted for a single nucleus. However, when we observe a large number of nuclei, their behavior becomes very predictable. When you talk about nuclear stability, it depends strongly on the number of protons and the neutrons in the nucleus. For example, isotopes have the same number of protons, so they are basically the same element, but they have different numbers of neutrons. For example, carbon-12 is stable, while carbon-14 is radioactive because it has unstable neutron-to-proton ratio. On the other side, isotones have the same number of neutrons but different numbers of protons. Although they are less common in basic applications, isotones help physicists to understand how neutron number affects nuclear stability. Professor, everything is clear about isotopes and isotones, but can you please explain why nuclei become unstable?
Okay, guys, give our professor some rest. I can answer this question. So why does nuclei become unstable? Well, inside the nucleus, the strong nuclear force holds protons and neutrons together, and this force is extremely strong. But it only acts over very short distances. And as nuclei become larger, the repulsive electrostatic force between positively charged protons also increases. So when this repulsion becomes too strong, the nucleus becomes unstable and radioactive decay occurs. And of course, we have 3 different types of radioactive decay, and I will let our professor, after she finishes with releasing radioactive substances, explain it further.
Oof, this was a nice radioactive release. Now let's continue with alpha, beta and gamma decay. Alpha decay occurs mainly in very heavy nuclei such as uranium. An alpha particle is emitted consisting of 2 protons and 2 neutrons. Because alpha particles are massive and highly charged, they ionize matter very strongly but travel in very short distances. After alpha particle decay, the mass number decreases by 4 and the atomic number decreases by 2. Beta minus decay. In beta minus decay, it is important to point out that neutron inside the nucleus transforms into a proton, and electron and an antineutrino, which is the antiparticle partner of the neutrino, meaning that it has the same mass but opposite charge to neutrino, both of them are emitted to conserve charge and energy. As a result, the atomic number increases by 1, but the mass number remains unchanged. When we talk about beta plus decay, some changes occur. A proton transforms into a neutron, but a positron and a neutrino are emitted. The atomic number decreases by 1, while the mass number stays the same. Last but not least, gamma radiation involves the emission of high-energy photons. It occurs when the nucleus loses excess energy after alpha or beta decay. Gamma radiation does not change the structure of the nucleus, but is highly penetrating. Even though alpha, beta and gamma are all forms of nuclear radiation, they interact with matter in very different ways, which bring us to their ionizing properties. Ionizing radiation is radiation that has enough energy to remove electrons from atoms, forming ions and potentially damaging biological tissue. Alpha, beta, and gamma radiation are all ionizing, but to very different extents. Alpha radiation is the most ionizing because it has large mass and positive 2 charge, allowing it to strongly interact with atoms, but this also means it loses energy quickly and has very low penetration. On the other side, beta radiation is less massive and has a single charge, so it is moderately ionizing with medium penetration. Gamma radiation has no mass and no charge, but very high energy, so it ionizes directly and much less frequently. However, this allows it to penetrate deeply into matter. This inverse relationship between ionizing power and penetration explains why different types of radiation require different shielding materials.
Okay, now we'll talk about radioactive decay and half-life formulas. And radioactive decay follows an exponential pattern, and it is described by the equation. And in this equation, N represents the most undecayed radioactive nuclei remaining at time t, while N0 is the initial number of nuclei present at the start of the decay. The symbol E is the exponential constant, showing the decay is a continuous process, and lambda is the decay constant, which represents the probability that a nucleus will decay per unit time. It is the time taken for half of the radioactive nuclei to decay, and it is a constant value for each isotope, independent of external conditions. The activity of radioactive sample is given by the equation A equals lambda N, where A is the activity of radioactive sample, that is the activity measured in becquerels, and it represents the number of decays per second. This equation shows that the activity depends directly on the number of undecayed nuclei. So as the number of nuclei decreases exponentially with time, the activity of the sample also decreases exponentially.